The addressing structure of the machine was by half words. And so you would really have to, in order to use the index register, would have to go down from 20 to 0. So so in order to store the thing in A sub, and this loop is going down, I really wanted to store in A going up, so I had to compute 20 minus n, and that's what this computation is here. So it's q equal to 20 minus n. Glenny's language, if you started with a plus sign, it was a normal instruction, but if it didn't start with a sign, it was an index register instruction. So here's a way to get from the index register into a normal variable, and then compute on normal variables, and then go into an index register again. Then subroutine 5 is the input subroutine, and this reads a value, and then we store it in A sub q. Next slide shows the rest of the computation. The output calculation and output was handled by subroutine 3 and subroutine 4. And here we have the test A is again the test on a sign, and a control is a go-to. Control X meant go-to X, and here's X here. I don't think this shows any other features of Glenny's language that we haven't discussed already. We test whether Y is greater than 400, D was a constant 400, and if so, we go to Z, and so we have two kinds of output. Subroutine 4 was the one that would do a carriage return, and we had to calculate I separately from n, the loop variable, because n was twice I, and there wasn't an easy way to divide by 2. So at the end of the language, then it says write 2 and start 2. That meant the main program is 2. Though this entry A, control A is something that relic of the good old days. This was a so-called. This says label A, go to A. This is what they call a dynamic stop, which was the way of saying that the program was done. An infinite loop, which the operator would recognize. Okay. Now the next slide. I'd like to show what was happening in America now at the time, and here we had something which people called compilers. But they aren't the same as what we call compilers now, as you'll see. Since I'm running short of time, I'll just get into A2 language. It's actually, there was a lot of talk about it and how this was the computer doing all the work of programming for you. But in fact, they never mentioned what these compilers actually looked like inside, and I'll show you what they look like. Next slide. First the programmer would assign his working storage, and then the first statement here is read from tape 2 in a special sequence that you would, if you wanted to do input, you would use generator for input, GMI. Here was in order to do an assignment, you could use the move generator, and this would move location 180 to location 216. Now the working storage was actually numbered 0 to 58, except in a move it would be numbered 180 to 2. It was absolute locations in the move instead, but relative in the others. Next, we have an example of some of the statements in A2 language. It was a 3-address type of a code, which the compiler would generate into direct instructions. And since there was no absolute value, I just squared it and took the 4th root. Well, let's go on to the next slide. There was no way to test inequality in the language. So you could supply your own code. You could supply UNIVAC C10 code for this and write a 3-line subroutine, these next 3 lines here, which would be a test on the sign of the argument. And then you specify the arguments here, T and label 10. So it involved a rather complicated sequence of things for the program. And the program had to also count these things sequentially, 8, 9, 10, 11. Notice the number 9 here, number 8 there, number 11 there. The compiler checked that you got those right. They were going on. Next slide. Here was a case where they had a built-in subroutine, so you didn't have to write it in own code, but you had to supply this many arguments. This was a test of, this was the iteration statement. Okay, that's A2 compiler, and it was somewhat improved by 1955, but so that the program could be somewhat shortened, but it never really resembled a high-level language. I just wanted to show this because it was called a compiler. Next slide, please. I'm so short of time, I'm afraid I'll have to start going fast. Lanning and Zeiler algebraic interpreter, we heard something about Lanning and Zeiler, excuse me. Let's take a look at their language. Their language, for the first time, you could write constants right in the code, and also they had very natural-looking algebraic expressions. If you look here, you don't write multiplication operator. You had superscripts that was part of the character set, and a subscript was with a vertical line and then the subscript. So A sub I is given here, and as we see then that when we had an existing precedent of mathematical notation, people strove for that. When we didn't have a precedent, when we had the control operators, then we have a wide variety of things. Here the CP1 says is a branch conditional if the last computed result was negative or not. SP was a direct go-to statement. There was no do statement, equivalent of a for or do statement in this language. But this system showed that a very high-level language even had built-in differential equation solver mechanism. You could say dy equals minus x and so on. It was implemented for the Whirlwind machine, and although it was called an interpreter, it really compiled into machine language code. The machine language was not just a bunch of calls on subroutines, though. Now, the next slide shows the beginning of Fortran. In 1954, from the beginning of 1954, John Backus began to work with some other colleagues on development of a Fortran language, and I give the name Fortran 0 to the language which was the first output by the group in November of '54. The next slide shows Fortran 0. The difference between Fortran 0 and what we have now is primarily that there's no format yet in input-output. That was a later invention. The do statement had three, you could give three statements here. It says do 3 through 8 and then go to 11. And you see the if statement was different. You could write your relation in here. And here's another thing. It says go to 2, but that's from the middle of a go to, from a do statement going to 2 would not start the do loop again, but it would say go to the next iteration. Well, that's Fortran 0. I'll have to go very fast now, I'm afraid. But there's a few more steps, in fact, and I guess they said we could take off a few minutes off the coffee break, Kelly. Now in Russia, Brooker, yes. In Manchester, we had the Mark I autocode, which is a much cleaner language than Glenny's, and the idea was to be machine independent. Let's take a look at the thing in Mark I autocode. Here the variables had to be named either n or v. The n were the integer variables, and the v's were the floating point variables. But and the star here meant output. But this language also was a three-address code because you had to build the formula in a long sequence of steps. But it was a successfully used language for a long time. And this J1 here, in parentheses, means the compiler does it now. This is the first time we have an example of a job control language in the same as the compiler language. It says now jump to 1. Next slide shows the in Russia we had what they called programming programs, and for short we call it the Russian PP. And these Lubinsky, Kaminin, Scherber in '54 and '55 developed the program for the Strela 2. I'll give you a next slide shows the high-level notation is Lyapunov's notation, and it's equivalent to flowcharts but much more compact. This branch here says go to 6, and then here it says coming from 4. This says go to 6 on true. R4 is a relation. The programmer would define his operators 1, 2, 3, 4, up to 14 in this case, and there were different kinds. R was a relation, A was arithmetic, Z was a hint to the compiler for saving code, and N was a machine language extension, and so on. Next slide. We haven't got time to go through this. The programmer would allocate his constants and working storage. Next slide. Then here's this operator notation repeated again from the previous slide. And for each, you'd first go through all your R's, then all your A's, and all your Z's and your F's and so on, and give the commands. And they developed a good parsing mechanism. The main interest in this compiler is the first time we had a discussion of efficient object code generation, removing of common sub-expressions automatically, and so on. This is a relation statement, says if C3 is less than V2, go to 6, otherwise to 5, and so on. Ust means stop. Okay, next slide. Now Yershoff, slightly later, was working on a program for the Bessem computer, and the next slide shows the difference in his language. Primarily, that we have all the operators can be written in context instead of separating them out and numbering them and so on. And here we have input statements in machine language. Then we have the loop, and vid means convert to decimal and output it and so on. But his language was quite compact, and I don't have time to give you more details except to say that this was of the same flavor as PP2, but much improved in its in the user interface. Still, in order to get this into a machine, they had specialists who would take this and translate it into numerical language that they could do input. Okay, next slide shows West Coast development at Boeing. Backache meant Boeing Aircraft Corporation Algebraic Interpretive Computing System. And the next slide shows how Backache looked. This was actually this was a very unusual language. It didn't have any iterations except to the end of the program, and the star was used for assignment. Well, you have to read the paper in order to see the peculiarities of this, but 2 meant equation number 2. So this would say K2 minus X is stored in place of equation number 2. Next slide shows Bloom's language. This was also done at the Naval Ordnance Lab, and Bloom's language is the first example of a declarative language rather than an imperative language. The declarative language, Lisp, came out in 1960. This is somehow related. You didn't have to give the things in order of computation, but you just gave the relationships that you were interested in, and the machine figures out which order to compute them. It's a kind of a curious language because he tried to base it on, he used Polish notation, you notice, and I tried to base it on recursive function theory, but he wasn't able to handle recursive procedures as we now understand them. Next slide shows the first language that I knew about when I wrote the other paper. This is the IT compiler, and it's the first really successful compiler. This is a landmark in the first time that a compiler was implemented with a lot of user ideas in mind, and it was used for many years in the life of the machine in 650. The next slide shows IT language. Had no precedence, and subroutines were given with this notation. Your variables were called y sub I, c sub I, or integer variables. And here's a go-to statement. It says do down to statement 3 for I1 varying from 10 steps of -1 to 0. And not too hard to read. The next slide shows Fortran 1, which came out after 18 man-years of work. Next slide shows that here we have a big innovation, a comment for the first time. Nobody thought that it was necessary to comment before in the language. And also the important innovation of format, the first time the person could describe the way his input and output were going to look. And this was, I think, one of the big reasons for acceptance of the big acceptance of Fortran on the 704, because it was very difficult to do the I/O conversions. Next shows UNIVAC's development of a language similar to Fortran, but with more English language usage. The next slide shows mathematic language, and at the same time Flowmatic was being developed, which is one of the predecessors of COBOL. So you have use of English constructions, and they also had superscripts in there, so on their typewriter, and absolute value brackets, and so they could do things like this. The next slide shows something which I don't have an example of the language, but Samuelson and Bauer had worked out at this time a language which could actually be directly input to a machine and interpreted on the machine. Now I'd like to finish by just saying that the work of Samuelson and Bauer and Rudeshauser in Europe, combined with an American group of the ACM, the next slide, led to the International Algebraic Language, then later called Algol 58. And I'd like to close just by showing what TPK looked like in Algol 58. The interesting things are that the declarations could appear anywhere, and you had the way of specifying input and output in this way, and the if statement was not done with if then, and the for statement wasn't done if then. It looks more like PL1 convention. Well, excuse me for going a bit over time here.
Thank you very much, Don. I'm going to take 2 questions, only 2.
Cuthbert was first.
Yes.
Well, I would say Cuthbert was first, and then Fritz Bauer.
Go ahead.
I have a procedural question.
Yes.
You've said, Don, that much of the paper is based on unpublished works which you have collected.
Yes.
Question 1, do you expect to submit these unpublished papers as appendices? And question 2, does the organizing committee hope and plan to accept such unpublished papers as appendices?
Well, my plan is really to write someday a coffee table book which includes a lot of unpublished things of this kind, and I'm trying to get IBM to sponsor it. And I've had some thoughts on this line, but I'm gathering not only on programming languages, but on a lot of the classical computer science techniques. I find that very often the work being ahead of its time was never published, and I've been building up a collection of these things which I do want to publish sometime as a source book in computer science. Harvard University Press has a series of source book on chemistry, source book on logic, source book on mathematics, and I'm thinking of a book of this kind, so I would wait with that.
Steve Rubin, Los Alamos and Carnegie Mellon. You noticed that the comment was a great innovation. One thing that didn't show up was, when was the first time that you were allowed to have variables more than 1 letter?
Yes, in Fortran 0 you were allowed 2 letters for variables, and then in Fortran 1 they allowed you up to 7. But the original Fortran was restricted to 6. Excuse me, 6.
One more question, Professor Bauer.
First, it was interesting to see in von Neumann's flow diagrams that assertions were carried with, and that in fact the method of invariance was used effectively in von Neumann's flow diagrams. At least it could be used. That's and right. It was foreseen.
That's right.
Second, for Rudeshauser, I have to correct slightly your program. Rudeshauser probably had never written A sub I 4 times. He had evaluated it once. This was possible, of course.
Yes.
And he knew exactly about the runtime efficiency to be influenced by proper writing of the formula.
Yes, that's in the Russian program PP2, there was a black thing in there called Z2, and that meant don't take A sub I wherever it appears and move it into a working storage. That was a directive where the programmer could write A sub I, but he could also tell the compiler to simplify that for him. That's quite right about because Rudeshauser's treatment of the subscripting would recalculate it several times and not using the index.
And as well, using a subscript within the formula was later considered by him seriously, and he would certainly have written it in this way without even making use of a machine instruction.
Oh, okay, thank you. The first point that you made about von Neumann's assertions it didn't appear in the close-up that I gave of flow diagrams, but it does in the paper show the example of how he had the fourth kind of box, which was the assertion box, which was an important way of showing that whenever you get to that part of the flow chart, this holds, and therefore the program is correct, since you just have to make local verifications.
Before we break, some brief announcement. Those who are flying to Albuquerque on the Ross special flight must get to the bus immediately after the meeting. The bus will leave here at 12:05. Also, the following people should report to the message desk as soon as possible if they do not want to walk to Albuquerque. Attention. Cardwell, Backus, Husky, Lavington, Wilkinson, Larson, Lubert, and Stern. And finally, please check the message board during the break. And on behalf of all of you, I would like to thank Don Knuth.